In June 2015, I went to Sheffield and I saw a paternoster lift, an obsolete design of elevator with a looping chain of open cabs. In June 2016, I travelled to Genoa in Italy and I saw an elevator that also moved sideways, except, spoiler, it's a bit of a cheat. It's actually a little horizontal car that moves inside a bigger elevator that does the heavy lifting. And now it is June 2017, and I'm in Germany at the brand new ThyssenKrupp elevator test tower, and they have flown me out here to show off Multi, their actual, full-size, working elevator that moves sideways without cheating.
For us, it was very important to have a tower to test the new technology. We don't want to test it at the customer side. The tower is 246 meters high, and this means 1,700 steps. I know that exactly because I walked up once.
This is a building made almost entirely of elevator shafts. Some of them test regular lifts, but some of them are reserved for this new system.
The principle of having a continuous rotating flow of cars was one of the best inventions in our industry ever. And to achieve this, we have to exchange cabins from one shaft to another. And to have this exchange, we need an exchanger, what you see just behind me. And this exchanger allows us to go into horizontal movement. The exchanger can be placed at every point in the shaft. So it allows us to do all kinds of configurations, coming down vertically and then going into the horizontal movement.
One of the problems with elevators in really tall buildings is that you need a cable so long that it can't support its own weight, let alone the weight of the cab that's then connected to it. The solution here is a bit different, and it doesn't use cables at all. It uses linear induction motors.
Linear drive, it's also a synchronous motor with permanent magnets. And you maybe know it from a rotating motor. If you just take this motor and cut it on one side and just lay it on a table flat, then you already have a linear drive. And this is what we have vertical and also horizontal.
In a regular elevator, it's called a traction elevator, you've got cables holding the cab, any one of which can hold more than the design weight. Also, you've got emergency brakes, which will pop out and slow the car down with friction if it's moving too fast. An absolute worst case, even if all that somehow fails, you have a buffer at the bottom that should reduce a free fall drop from fatal to just severe injuries. Elevators are incredibly safe because they're incredibly well regulated. So before this is allowed to carry humans, this system needs to be at least as fail-safe.
The safety is not just in the ropes of a conventional elevator, but in the brake system. In conventional elevators, you have the brake on the machine, on top of the shaft in the machine room. Now we have the brake directly on the cars. This new component, the exchanger, where we go from vertical into horizontal movement, also needs to be checked by our safety controller. What is the position of the exchanger? Is it locked? Is it safe? And in case any violation of a safety rule, then we go to a safe state.
There are, of course, some catches. Linear induction motors are expensive and heavy. Each one of the cabs needs to have its own set, and the whole elevator shaft from top to bottom needs to be lined with the magnetic coil units that power them. To save weight, these cabs are made of carbon fibre and aluminium. So will it work out in the real world? ThyssenKrupp's models say it will, but once everything's been tested and approved here, the next step is to sell it to the kind of enormous multinational companies who build skyscrapers and who do not like risk. And that might be a greater challenge than making the elevators in the first place.